Hi, Charles Bailey here from Navitas Semiconductor, talking to you today about four segments starting at the system level and how our components, wide bandgap silicon carbide and gallium nitride, have a value proposition in all of those systems and segments, and we will do it in the context of past and present. So here we're starting with the data center display, and what you see here is a standard 42U rack with two sections in it. And in the bottom here we have circa 2003 high performance computing standard, which at that time was UP and DP, uniprocessor and dual processor servers, an LGA Xeon kind of golden standard, and this represented at about 0.8 teraflops floating operations per second in that era, and that had a corresponding power density for the power supplies and also an efficiency standard. Except in 2003, when this was launched, there was no 80+ efficiency standard. That came into being right about that time. So the efficiency of these power supplies quite a bit lower than what we'll talk about today, 2003 era, and also moving into the future. Okay. Also the power density quite a bit lower. So around 30 watts per cubic inch, maybe as much as 35 watts per cubic inch in that era. Now today, what we have represented here for 2003 golden performance standard in computing, the NVIDIA Grace Hopper 4U and 8U GPU-based server systems. So these approach 30 teraflops, okay, which is a significant, about a 50 times increase in computing bandwidth over the last 20 years, as we know from the data center industry. Here, the power jumps up considerably. So the power density also has to increase. That's where wide bandgap assists in being able to do that. We'll see in just a moment. Now, as you can tell from this rack, right, we want the rack to be primarily computing power, also storage, but not a focus on the power supplies itself, therefore driving higher power density. Also, what are the two main drivers of cost in the data center? Number one, the cost of electric power, and number two, the cost of removing waste heat, power dissipated. So if you don't dissipate that power in the first place, if you have more efficient power supplies, that burden becomes lower, and of course, with more efficient power supplies, the cost of electric power itself diminishes. Now, we've talked about the last 20 years of the computing industry sort of gold standard. What's happening moving forward? Well, we're approaching a cliff, as it were, in processor power consumption and the required power density and efficiency of the power supplies. So here we have graphed Moore's law on a linear scale. So normally when you see Moore's law, it's on a log linear scale. It appears as a straight line. In reality, the level of integration stayed flat for a long time. We didn't reach 1 billion transistors until about 2008. And where we're headed today, the NVIDIA GPU stands at 54 billion transistors integrated. And with wafer scale processing moving into the future, we will be having 2.6 trillion gates integrated into the processor and beyond. All this is driving an enormous amount of power. So the efficiency and the power density of the rack power supplies has to improve. Now we get to where Navitas is already being designed into and moving into production in CRPS, or redundant power supplies. So back here we have a silicon power supply. You can see the size of it. It's only 2 kilowatts. And this is kind of typical, say, 2020 type or 2021 type power supply that a system integrator could get off the shelf. So silicon, 2 kilowatts. And here we have an all GaNSafe or gallium nitride based 3.2 kilowatt power supply in almost half the form factor. So here we have the industry's first 100 watt per cubic inch power density, also with titanium plus efficiency standard. Then we move to, okay, in the same form factor, we go to 4.5 kilowatts. So about a 45% increase. How? By making a hybrid power supply. This is one of the unique things about Navitas Semiconductor. We are pure play wide bandgap, silicon carbide, and GaN. So we're using silicon carbide in the PFC in this, which is a very good high temperature, hard switching power transistor. And we're using still the GaNSafe in the DC to DC section. So we get a very high power density. We also get very cool transistor operation in the front end. So we moved from 2 kilowatt silicon to 3.2 kilowatt GaN in half the size, and up to 4.5 kilowatts with a hybrid power supply.